Okay, so I guess I'm live. Um, Today I'm gonna be implementing the exponential function in C. Um, it always you might just be using these functions, not never thinking about how they're actually implemented. But it turns out that a lot of them are pretty easy to implement. Um, Originally I was gonna do the natural logarithm, but I realized that the method I'm going to be using, the Taylor expansion, is actually very bad for natural logarithm. It's only good for natural logarithm where um, the value that you're calculating the natural logarithm for is between -1 and 1. For calculating natural logarithm of x greater than 1, you need to use a different algorithm, which I will look into a little bit more, and then I'll probably do the same thing. So, got a new folder here called NIH, because, seemed like a funny name. We'll just init that one there. And then I think I'll make a subdir called math. And then we will start. So what we will be using today to calculate the natural logarithm, not natural logarithm, to calculate the exponential function is the Taylor expansion of e to the x, which is actually a decent method for calculating the exponential, except for if you are going to subtract 1 from the results afterwards. If you want to do that, you don't want to use this method because you can run into floating point precision errors, which causes that to be kind of a useless calculation. So we won't be using. Well, I might write the same version. It's really easy to extend to the exponential -1 case. Um, Oftentimes, I think it's even provided as like a separate function. So yeah. So here we go. expm1. Yeah. This function shall compute e to the x. I'm not sure what this typesetting error is. E to the x -1. So it exists specifically because there could be like a precision error if you subtract 1 from the result that you calculated for e using a Taylor expansion. So let's start. So we're just going to do it in floating point. Can be easily extended to double using the same method. And let me just find here the Taylor expansion. So I'll just drag this over here. Where are we here? So Taylor expansion of e to the x, given, or just in general, without deriving this, it's really easy to derive based on it's like the geometric series. But anyways, I can't actually remember now. Anyways, so this is our equation that we want to just implement. It is basically one. Let me just say here. So in my typical fashion, I'm just going to do this immediately, though maybe I should make a separate header that just gets included in all these functions. But for the time being, we'll just do this. And then get rid of this window. So interesting. So what we want to do is calculate e to the x. Let's just actually type it like this. Oops. Where using the Taylor expansion about x is equal to 0. So it doesn't really matter in this case. Let me not type this like this for now. Yes, hello, R. Miller. It is indeed a calculus thing. So when you want to go and compute something on a computer, like any of the special math functions, including sine and cosine and whatever else, you're getting Vietnam flashbacks. This is basically the only method you can use to calculate this, or you can express it in terms of other functions, which you would. Oh no. Yeah. So when you take calculus, I don't think Taylor expansion really makes any sense to you, or like why it would be useful. But when you go to implement stuff like this in code, the Taylor expansion can come up. So add a comment here for now. X to the n over n factorial. Yeah, of course. So the nice thing about using this method though is I'm gonna get it wrong for sure, but basically there's a fixed amount of precision that a floating point value has, which basically means you only need to calculate the number of terms up until that precision, and beyond that it's pointless to calculate any more terms. So it's actually not it's actually not so crazy as you will see. 32 bits, it's 11 digits after the decimal point. It's not quite how floating point values work, so let's just go to the IEEE floating point Wikipedia thing. Nope, not this one. Zoom this out a little bit here. So it actually depends on which floating point value you're talking about. It's not like a fixed precision thing. Yeah, exactly. No one likes dealing with that IEEE floating point standard, but it's what we have to deal with. So for floating point, it could be down to like 10 to the minus 20 if you're dealing with these really small values, or the precision can be really bad if you have like a really big value. The precision's only 10,000, but very bad. Yeah, you could implement this with like fixed point integer calculations, and then you could be like, if you did that, you would have like a very well specified precision. But since we're using floats, we're not really going to have such a nice precision. I guess down here, this thing kind of tells us here. The fraction has like 23 bits, but then you have like an exponent that's 8 bits. And it's like a signed 8-bit number, so it's like you do like a multiplication by like 2 to the minus, like in the range of 2 to the 127 or 2 to the minus 127. So fixed point is good. It's just that computers have been optimized to calculate floating point values rather than fixed point values. There used to be computers that had like instructions specifically for doing fixed point calculations. I don't think that's true nowadays. I'm not actually using Vim. I am using this, which is different editor. It's like VI plus SAM. So it allows us to do like some funny regular expression type editing, which I probably won't be using today, but anyways. So F32 expf, and this will take an F32x. Probably this is fine. And at some point we're going to have some sort of result, and we are going to return that result. Oops. Yeah, I find that I'm not really a big fan of C++ besides like operator overloading for doing like vector addition and subtraction. Other than that, I'm not a big fan of C++. I guess what we can do is begin by initializing this to 1, because obviously we need this little 1 here. But there's a few things that we should consider, so I don't know if I want to consider them just yet. Oh, I use the proper string, like I use my own version of a string, which would be type def struct, and my kind of a string would be something like well, let's use these for now, even though I usually don't type that. It'd be a uint pointer data and a pointer diff key size or length len. This is usually how I make a string, and I call it like an S8. I don't like using null terminated strings either, because they're a very poor idea, to be honest. Well, this one just uses like standards, like you could just use standard C types for this. You could use like long and well, unsigned character is usually what I'm using, but rather than I mean for like certain Windows APIs, I guess, but I see. I mean, even all my Windows code, I don't really use like. I usually just I don't know. I've never had to like deal with the wchar thing in any of my Windows code, but I mean, I'm not like a primary developer for Windows, so if I was, then I probably would be using it a little bit more. So now what I'm thinking here is what I want to do is probably well, definitely probably make use of a for loop in some aspect here. The type here doesn't particularly matter, so I'll just do this. I is less than some value up here, which we will calculate. Yeah, it uses like SAM. SAM is like yeah, SAM is like the addition to VI that Vis has, I guess. That's how I would put it. For now, I'm just going to do this. So define iterations. And I should compute like a better value for this. But for now, let's just say we are going to do 16 iterations. I don't actually think we need to go that many. Like it might be less, like it might be like 10 or smaller, but I will just avoid doing the proper calculation for now. And then I'm going to also include in here a table of F32 let me say, well, I'll be a little verbose. 1 over factorial n. Oops, and it is going to be this, and we only need 16 of these because we're doing 16. And then what we want to do is pre-compute all of these values. So let me just think here. Yeah, they're the standard. Well, I guess it's like Linux kernel standard 8 with tab stop. When I started using like original VI, yeah, exactly. When I started using original VI, there wasn't like a configuration. It was just 8 with tab stop, so I never switched back to anything smaller than that. I'm just thinking I want to use this as a lookup table. So also this should be either n iterations or n iterations plus 1. I haven't decided yet, but n iterations I plus plus. You mean like very minimal like this, or you mean like Vim and Vim? I'm sorry, very minimal like VI or Vis and Vim or NeoVim, where you can configure like a ton of stuff. At least to me. Yeah, yeah. No, so this we have like the Lua API. So no. So this has like the Lua API like NeoVim, so you can actually do like a lot of crazy stuff. Like I haven't. Let me just. We're gonna need to like build this at some point, but I need a file to link this to, so I don't have a main function yet. What's it that you don't like about Lua, I guess? Um, like I've used Emacs before. I just didn't like I preferred the modal editing rather than Emacs like style. So we need 1.0 f. So definitely when n is equal to 1, that case is obvious. But I'm thinking about using the 0 case as well. So, oops. Let's not use the 0 case. Let's start this at 1. The Emacs pinky strikes again. So when n is equal to 2, it's just 0.5 f. When n is equal to 3, it's 1 over 3 factorial. So it's 0.33 times 0.5 f, which is 0.1666666666. Now how many digits I just need, I'm not 100% sure. 666. That's probably too many digits, but what is that? So we're on like, well, 16 to 31, like 15 digits. I think that's too many, but well, maybe Do you have like an ergonomic keyboard? You could try like using try that out possibly. Uh, okay, and then well, I think I'm just gonna start using my using a calculator to do this, but um scale equals let's just say 16 for now. And then we will do wait, can you do factorial in BC? Um it's definitely some functions in BC, but I do not know if they are even documented. Sine, cosine, arctan, natural log, Bessel function. An interesting one to include. um, so I think there's like max and there's like a list of functions that this has. Operators, keywords, functions. That's the BNF. I don't care about that. I just want to know what the actual functions are in BC. um, so there's definitely like why they're not like listed anywhere. That's annoying. Following functions shall be defined when the L is specified. Um, yeah, I think you can do that in BC. I just never bother doing it, but um, yeah, I can. I guess I can just do that. Um, yeah, define fact. Oh no, don't try to install Firefox or Chrome or Rust. Actually, Rust might be like the worst, and you'd need that to install Firefox. So, but anyways, thanks for stopping by. If you're heading out, uh, if x equals 0, let me actually know what the syntax for this is. Oh yeah, no, I know. I've been using Gentoo for like uh many years at this point, but yeah, Firefox and Rust and Friends are not so fun. me just see if, let me just check something here and like this. Yeah, it's not gonna. There's my old custom fetch nonsense. Yeah, I like OpenBSC. I use it on my my server. Did I just do something weird? Anyways, so BC function declaration. Guess I probably just need semicolons in my if x equals is there an f? I would assume so. Yeah, if express. Okay, yeah. So if probably we need brackets in BC, I guess. So if x equals 0, return 1. If x equals 1, return 1. Return x times fact x minus 1. This may be a problem if these are like floating points. Who knows? So fact 2 give 2, fact 3 should give 6. CWM, nice, nice. Possibly for integer values, but I was meaning to calculate 1 over fact 3. I'm not actually sure. So probably works good enough for what I'm doing. The scale equals. Oh, actually, that's a good point. Yeah, you're right. Yeah. Yeah, maybe it does just use arbitrary, like, fixed point precision for everything. That's possible. 3 days. So actually, on this system, I completely eliminated GCC. I just use Clang for everything. That's because I'm not using glibc. Oh, Clang is definitely worse for compiling. Oh, what do you mean? You mean for compiling, or you mean for? No, I don't use GCC on this system. I don't even have GCC installed. Uh, nah, there's no GCC installed here. Oh yeah. It's definitely worse for compiling. Yeah, I'm using Musil as well. It's worse for compiling, but it does it's a much better compiler than GCC, at least in my experience. So 1 over fact 4. And we're just gonna start copy pasting these into here. And 1 over fact 5. Probably use 0, though it doesn't matter at all. 1 over fact 6. I should group these better, to be honest, so that I can see how many of these are, but okay, let's do it this way. 1, 2, 3, 1, 2, 3, 1, 2, 3. This. Yeah, KSH is pretty nice. No particular reason. Because I'm like looking at the basically because I'm looking at my 80 column thing here, which doesn't really matter, to be honest. But yeah, you are right. Groups of 4 would be a little bit nicer. Oops. Definitely with like the amount of zeros that are just showing up now, I'm not sure like I need this many terms, but wait, I like missed. Did I skip one? 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Oops. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 15. 1, 2, 3, 4, 4, 8, 12, 15. No, there should be 16. There should be 16 elements. Oh, because I see what you're saying. Yeah. Okay, I'll just make it 15. Streaming and talking makes counting hard. Yeah, that's true. I'm not gonna fix that right now. So result plus equals x times 1. The only thing is like this x, we need to calculate x to the n. This is definitely not the best way to just be doing this, but j equals n, j greater than 0, j minus minus. I don't see why they wouldn't, but yeah, I don't see why it wouldn't. So like, I don't even think ButterFS is like necessarily that optimized for like solid state drives. It has like some options for it, but I minus one. So let's make a new file here, which will include print standard io.h, and it will include bxpf.c. Well, we're just gonna write a test here to just print out some values and see if it looks reasonable or not. Though I could also just test it. Um, should be like consistent about my style, but I don't know. So which part of my style is bothering you? Is it the return type on a different line, or is it this bracket on a different line? I will say I learned well. I don't think I have the OpenBSD man pages just installed on this system, but man.openbsd.org KNF Hungarian notation. No, no, no. I'm not a Windows programmer. What is the is it like style? What did they Oh yeah, yeah, yeah. So I think this is like pretty similar to OpenBSD style, but I could be wrong. I haven't. Oh, it is. This is OpenBSD style as well. Kernel normal form, as they call it. And go along with the rest of my. um, e to the uh, this is like the worst way of just testing this, but oh well. Um, sure. Well, I don't even need to do that. I'll just do cc test.c. And it's gonna complain for me doing what? Oh, oops. That was dumb. I meant to put I here. J equals I. And oops. I'm gonna just write my build.sh so I can fix this in my um and don't want to do that just yet. Test. Okay, so now we can do this properly. And I can just do this and /test. Wait a minute. That doesn't make sense. What am I doing? /test. Okay. Cool. Yeah, thank you for stopping by. Have a good rest of your evening, I guess, if it's that what time, if it's that time where you are. Right. So this thing. Do they not have? Does BC not have exponential? Huh. Good question. I don't want to do that. So maybe I can do that. Huh, okay. Thought this was one of the functions they just had. Maybe it's just E. Oh, you have to invoke it with -L or note that such a function is predefined if the L option is defined. I forget what like the L option does. Oops. Define the function and initialize scale to 0 and set default 0 C extended. But I thought that you could change this in the. I thought you could change this while running though, but maybe not. So that's fine. I don't need the. You don't need the factorial function right now. So we're already on like a good-ish. Let us edit this so that it prints more random numbers, even though well, we said 16, but I don't think it's accurate to that many. But that's fine. Sake of okay. 85525. So actually we've got like some inaccuracy, so maybe we need like a few more values for that one. E to the 1. Now 71812 818 is what it should be. Actually that's higher than what it should be. Weird. Did I like define this function incorrectly? That is possible. I don't think so. So maybe I need to calculate pre-compute more factorials. Wish I could clear the screen in BC. I cannot. So I'll just redefine this thing. So let us increase this to a big value. I want to. There's a way of increasing this accuracy without just doing this, but and also maybe I should handle the edge cases first. But I don't want to just do like what. So for example, I've looked at like the muscle library implementation of this, and for some reason, even when you're computing integer floating point precision, they'll just use doubles everywhere, which isn't really fair, to be honest. And it's also not really like kind of dumb. Like they're basically just saying that you need a double precision float if you want to compute this, which is kind of dumb. But even though you're just computing single precision. And they also do like a bunch of nonsense with like oh they go like big. Wait, but there's like a polynomial that they're using. Interesting. I wonder what this where does this polynomial come from? Wait a minute, where does this polynomial come from? This polynomial, I don't even know if it's A and B are complex. We're not doing that one. Hmm. Where does this fraction, this polynomial, there's like a polynomial representation that they're using that I've never seen before. Interesting, interesting, interesting. So the I'm just gonna copy this comment so you can see what I'm talking about. So they are saying that what are these like C values? Yeah, I don't know where they where this is coming from, to be honest. I've never seen this before in my life. Um well, I mean, I'm not a big fan of their method of doing this either, to be honest, of Musil's method. So they just have this again. They're using like doubles everywhere, and UN 64s. I mean, it's copyright like ARM, so I don't know who someone contributed this from ARM, but I'm not a big fan of that because they're like it's kind of cheating. They're not actually computing the thing that they're this table that's got a ton of just doubles in it. Exponential f is including which? Exponential 2f data.h. What? Yeah, this is not I think they're using this is like some special function that I have no idea, never seen before in my life, but um especially because they don't even say what r is. Like, what is r? Or k for that matter, but they're those ones are uh, where did z minus kd? Val is double z plus shift. Yeah, I don't know. The standard library version of this is very cryptic, to be honest. So I don't know if I want to just add more iterations. I think that's not the issue though, right? I think the issue is that some of these values that I've computed here are not like accurate enough. Because let's just see, like, if we just make these go back to like our 15. And let's do this. Just because this is annoying me. It should be like a macro to do this, but anyways. Okay, so fact 1 1 over fact 3. I think that's like still the same. Oh, it's more. Okay. I also thought that if you just kept doing this, eventually the compiler complains at you for having no, I don't know when the compiler complains to you. Also, I don't think that this is really the best way forward, to be honest. But yeah, I don't think this is actually. I think this might just be like how like what I can do actually is rename this to NIH. And we're just gonna do a comparison here with the standard library one. So include math.h NIH. There is like a little bit of a delta here. Um, but both of these have like a delta from the BC arbitrary precision, right? So if we just like compare those, and actually I'm not even sure. E1 minus this, actually let's do the other way. This minus, because it's greater than E1. So that's the delta for that one. And then for the standard, which is less, okay, so like the delta is like a little other. So this one is like about twice as accurate standard as the current version that I just wrote. Now, on the other hand, the one that they're using is, put it this way, I think like if we just add a couple extra, no, because adding extra terms, like it's already greater than the thing, so if you just add extra terms, it's not gonna shrink it ever. I wonder if taking less terms would minimize the error. It's an interesting thought. It's definitely possible. We can try that. So technically here, let's make this 15. And then just lower this to like 12. Still gonna do the same thing. It's just not gonna add a bunch of extra junk. But did I even... Interesting. So those terms are not even contributing at all to this error. So I should also just look at the disassembly to make sure it's not doing something weird behind my back. But I'll do that in a second here. So, I mean, that's definitely possible if we do 9. Yeah, it's actually worse. Let's open this. Let's take a look at the output assembly. Oops. So we load the register. Is this? I'm not sure what this actually instruction is doing, but that's fine. Everything here is just exactly, I don't know why it had to put all this stuff out of order, but it did. In any case, everything here is as expected. Oh, it does. Okay. Okay. It does call that function. That's good. Um, no, why this loop is like partially unrolled, I'm not sure. I can go back to the old O0 and hopefully it doesn't do stupid stuff like that. I mean, it's not stupid if you want a fast program, but it's stupid right now when I'm trying to actually debug what's going on here. um, I mean, now this is just going weird, but why? Who knows what the compiler is doing there? It's fun. Um, okay. Oh, I think I was just dumb before. I think that unrolling was fine. But everything else looks good to me. Um, oh, interesting. It doesn't use. Why did that like switch what was output there? That's really weird. On O3. Oh, G. So let's actually just go here. So it looks like though that 12 is gonna be the best case. 12 is more than sufficient for this specific method as it is. Um, because if you just add more terms, we're not gonna get any more accuracy in like the higher order bits. Um, maybe like 10 or 11 is better, but besides that, um, need this. Oh, did I just do some nonsense? Well, that's funny. If you want like the most accurate, so 10 iterations gives you the. Let's just make sure now. Let's actually do this OBJ dump just to make sure it didn't do something unexpected. Um, it looks like we're still just doing what we're supposed to be doing. All SS, add, ink. Everything here looks about correct, so as long as we're still calling printf, normal exp. Yeah, that's interesting. So now if we go to here and actually check for some of these ones. Ooh, that's like quite inaccurate. What about the normal standard library one? Yeah, so it's like 1,000 times more accurate, 1,000 times closer to the representation given in here, which is not necessarily the most accurate either. Now there's another one I think I want to test is if I go to the intrinsics guide, I think there's an intrinsic for computing this in the special math functions section. Sure there is. Maybe not. There's definitely like a log one. Wait, what? Maybe it's not in the special math functions. Yeah, it's not in there. Okay, let's. Oh, interesting. There's like a complex one as well. Let's use the normal, not half precision. Where's the single precision one? Okay, let's try the intrinsic version as well. So let's open the test. And we're going to add another thing here. We're just going to int intrinsic. And I'll put that in this test file as well. So to do this, I'm going to need to do a load. Let me just copy this first. So that is the function signature for that one. And then we have to do some loads and stores. SSE, actually MMX is fine. MMX load. Okay, SSE load, fine. So there's load, load packed, load single. Okay, so we get here is an M128 temp T, it doesn't matter, is equal to mm load SS and X. This just to be somewhat fair, we're not gonna like, well, it doesn't really matter for this case anyways. This will just load a single floating point value into the lowest area of the 128-bit vector register. So there's like 4 floats in that register. And this will just put the lowest 4 bytes, the lowest 32 bits to be the value of X. And they don't need to be aligned or anything for this instruction. And then we're gonna get this back. So we're gonna do T is equal to this. Pass in our T here. And then we need to do a store. And it's going to be a store. Is there like store SS? I don't think so. Yeah, there it is. Never mind. Then we're going to do an store single thing again, and we're going to store it into X, and we're going to take it from T. So actually, I can like kind of compose some of this because, I mean, who knows? Doesn't really matter. but whatever. Just compose that. So there's our little very inefficient, not how you normally do vector instructions implementation. Just want to do it just to see how this built-in function actually does the calculation, because this also computes like a Taylor series. It's not specified necessarily what that Taylor series is. But otherwise it should be fine. So we will just do this and see how the result of this one comes out. Let me just make sure this builds. It doesn't build because why? Because for some reason that is not where it says it is. Sorry, not that one. It's this one. Yeah, why is that not where it's just supposed to be? And why didn't they give me a suggestion of where it is possibly? It's possibly in this header. No, this header would be included. Um, I don't know why they have to have this in the search path, but they do, so we're gonna just search for yes, right. Oh, interesting. That one doesn't seem like it's necessarily exposed. Oh, that could be a problem actually. So maybe huh. So actually that one might not exist in Clang. This might be like something that only exists on the Intel compiler. If I do like this, right? I'm gonna show like this macro thing. That is very interesting. Yes, this is actually an Intel's short vector math library, which does not actually exist. Good. Funny. Oh god. Why? So apparently Intel just like has a bunch of nonsense like that just mixed in with the intrinsics, and they don't tell you which ones are just in their library and which ones are not in their library. So that's funny. I actually won't be using that intrinsic then, as it turns out. Um, that's okay, because I'm not doing that test. That is okay. So, yeah, I don't know what else to do with that then for now. Um, Now, one thing I actually didn't check before was shouldn't have deleted those extra iterations, but do have those extra ones if I just want to add them back in. This would have been fact 12. Oh, we're just computing 10. I just want to see like the what's the error on like the second order term on the second exponential term if we do it this way. Versus this other one, the standard library one. Okay, so we're still like much, it's not as bad. That's really interesting. And then for like e to the 3, so e to the 3 is like quite bad. But then it's also going to be quite bad in this one. Oh, it's not. Okay. Huh. So there's actually some work that should still be done. So I guess it turns out that maybe this is not the best way of just doing this. Now the reason why, well, this does actually have more. That would indicate that more terms are actually needed, and it's only down here where they're like increasing the inaccuracy. That's weird. That's definitely weird. So yeah, this one needs more. These both need more. Should have checked before I removed like the old ones. So that was 12. If we go back up to 15. With it's okay. 1 over fact 14. Oops. And 1 over fact 15. So if we go back up to 15, what happens to those oh yeah. So this is actually getting closer now. Interesting. It's still like significantly worse. I'm like curious to do a little bit of research after and see if I can figure out um what this polynomial approximation is, because I've never seen that before. I'll have to look up possibly in I doubt Hacker's Delight has anything about this particular function. I mean I can look at it right now, but I might have to look up like some numerical methods books to just find it. See if there's like any math in here at all. There's some floating point stuff in here, but I don't think they show those functions. They do have like integer exponentiation, which I'm gonna check quickly in a second here. Oh, so interesting. I might actually want to go and look at like the Newth's textbooks to just find some of these formula. It's possible that that's where they're just coming from. So let me just see here. I'm gonna go to this integer exponentiation and see what they have. 288. So this is actually oh, I see. This isn't even like that interesting though. So because they just I don't get it. Maybe it's like more optimized. This integer exponentiation they're just showing is I see. So yeah, no, actually they're all they're showing here is in this book is that you can be like fancy if you need to do like x to the I mean I could use it in my loop if I wanted to speed it up. If you want to do like x to the power of well, I guess it only works with integers. It should work without integers as well. They're just basically saying you should. Oh, I see. Sorry. It's x to the power of an integer. They're just saying that if you have x to the power of an integer, then instead of multiplying x, like 12 times or whatever, you could have broken that down into like multiplying x uh 4 times and then squaring it and then like squaring that part and then keeping and then adding then multiplying the first part again by the squared part. So that's like it'd be like 4 multiplications and then 1, so 5 and then 6 instead of 12 or whatever. So yeah, that if you're trying to do like some really crazy optimal thing, that would be smart. But for these other things where we want just like some special it's e to the x stuff, I want to figure out what this special formula is that I've never seen before. Um, However, how long have I been up for, streaming for? An hour and a half. So I think that's pretty good for now. Close that. Um, so that's like a well, it might seem dumb, but let's leave it at that. This is like this is a good first pass, I would say. However, I definitely don't think we should need 15 times through this loop to just figure out this value. I'm curious what happens if you just optimize this though. If you build this with optimizations on. Let me see. Oops. What I wanted to do is that. Let's do this. Let's have a look quickly at the OBJ jump for this and see if it does some fancy stuff. Oops. Well, is it just completely unrolled? I think it's just completely unrolled. I think that's all that happened here. Wonder if that gives you the can't change the name of that right now. I wonder if that changes the results at all. Don't think so. Yeah, so I think what just happened there is it just completely unrolled the I think it just completely unrolled the loop. It looks about right. It just looks like it just completely because those were like a fixed number of so it was only 15 iterations, it just decided to unroll the whole thing. Yeah. Let me just take a look see at the stream. That's gonna be it for me for now. I will come back on probably tomorrow, and either I will implement this with if I figure out what the equation was that this special version of this came from, I'll implement that version. Otherwise, I might implement the logarithm. Now, the logarithm is a bit difficult and a bit different. So the logarithm, I won't actually use a Taylor, like natural logarithm. I won't be using a Taylor expansion because that one is not so good. But anyways, thanks everyone for watching, and I will see you all next time.